Hello, Calc 2 people. Welcome to section 7.4, Integration of Rational Functions by Partial Fractions. So this is yet another method to integrate, and it's pretty cool, so I hope you enjoy. Let's start very basic. Let's find the integral of 3 over x plus 4 dx. Well, the answer is, maybe you can just see this directly, 3 times the natural log of x plus 4 plus c. Right, well, how did I get that? Well, we could do u substitution. We let u equal x plus 4 and du equals just dx. So really what we're integrating is 3 over u du, which is 3, 1 over u du, which would be 3 times the natural log of the absolute value of u plus c, which in turn, when we resubstitute, replace the x's, we get 3 times the absolute value of x plus 4 plus c. Now this works nice. This is an easy template because we have no powers on x. Be careful, just because something appears in the denominator of a fraction, when you integrate it, it does not always result in logs. But in this case, when we have just a nice linear factor, the antiderivative in a constant in the numerator, the antiderivative is always just the natural log of what's inside the denominator. All right, so let's go for this guy. The antiderivative of 1 over x minus 5 is just the natural log of the absolute value of x minus 5 plus c. So you can take the derivative and confirm this. All right, so very basic Calc 1 type antiderivatives. But notice, if we are to add 3 over x plus 4 and 1 over x minus 5, well, we need a common denominator. So the common denominator would be, we would need to introduce the x minus 5 into this fraction, and we need to introduce the x plus 4 into this fraction. So we would land up getting, the left numerator would be 3x minus 15 all over x plus 4 times x minus 5. My right numerator would just be x plus 4 all over x plus 4 times x minus 5. And then when we add the numerators and keep the common denominator, 3x plus x is 4x. Minus 15 plus 4 is minus 11. And then x plus 4 times x minus 5 is x squared minus x minus 20. So therefore, if we were presented with this integral, 4x minus 11 over x squared minus x minus 20, we know that that's equivalent to, if we go into reverse, that's just 3 over x plus 4 plus 1 over x minus 5 dx, right? And we already integrated this. This is just 3 times the natural log of x plus 4 plus the natural log of x minus 5 plus c. So what we're trying to do is take more complicated rational expressions. We're going to learn how we can break them down into simpler rational expressions for which we can just integrate straightforward. So that brings us to the next page. What if we started with this? How can we break it down into those two fractions? Well, this is called partial fraction decomposition. So we have to, there's different cases. The rational function isn't in the integrand is such that the degree of the numerator is less than the degree of the denominator. We'll look at the other cases after. And the denominator has distinct linear factors. Then we set the integrand equal to constants over each of the linear factors. All right, what do I mean? Well, let's do this process. So we decided that this is going to be 4x minus 11. We try factoring the denominator. If we could work with linear factors, that's really great. And x squared minus x minus 20 is just x plus 4 times x minus 5 dx. So what we do is set 4x minus 11 all over x plus 4, x minus 5. So these are distinct linear factors. They're two different linear factors. We're going to put the first linear factor in the first fraction, the second linear factor in the denominator in the second fraction. And we're going to just put arbitrary constants a and b into the numerator. And now we have to add these together with these generic a's and b's and then solve for what a and b would equal. So if I wanted to, so forget this for a moment, and I want to add these together to create one fraction, I'm going to have to use my common denominator again. So this is going to be, I'll do it all out. This is going to be a times x minus 5 all over x plus 4 times x minus 5 plus b over, because this denominator is missing the x minus 5 factor, this fraction, this denominator is missing the x plus 4 factor. So it's going to be, right, so it might seem like we're working backwards, but you'll see as we progress how this really works. So we break it down, the denominator, we put arbitrary constants a and b, and then we solve for those constants that would give us, if we do add it, 4x minus 11. So the common denominator would just be the product of the two distinct linear factors. We introduced x minus 5 into this fraction in the numerator and the denominator, and introduced x plus 4 in this numerator and denominator. All right, so now let's clean this guy up. So let's keep going. Sorry. Disheveled here. All right, there we go. All right, so now my new left numerator is ax minus 5a all over the common denominator x plus 4, x minus 5, plus bx plus 4b all over the common denominator x plus 4, x minus 5. Now that we have common denominators, we can add the numerators and keep the common denominator. We get ax minus 5a plus bx plus 4b. Right? Now remember, this all equals 4x minus 11 all over x plus 4 times x minus 5. So when we get to this point, we are now going to take this numerator and set it equal to this numerator to find the values of a and b. So from this, we get that 4x minus 11 must equal ax minus 5a plus bx plus 4b. All right, so how do we do this? I'm going to rewrite this, 4x minus 11, and I'm going to combine my x terms, ax plus bx, and then I'm going to put my constant terms next to each other. All right, so a and b are the coefficients in front of x. So a plus ax plus bx must equal 4x. So from these, we get that a plus b must equal 4, because the coefficients in front of the x's must equal the coefficient on the right side, must equal the coefficient when we add them. Sorry, let me start all over. The coefficients on the right side, when we add them together, the a and b, it must equal the 4 on the left side. Now, the constants, notice there's no x's here. Negative 5a plus 4b must equal negative 11. So now we have this little mini system, two equations, two unknowns. We solve for a and b. However you want to do this, you can do substitution. You can solve for a and stick it in. I think I'll do that. If a plus b equals 4, isn't it true that a is equal to 4 minus b? So then we're going to put that in here. So we'll get negative 5 times 4 minus b plus 4b must equal negative 11. And let's solve for b. Negative 20 plus 4b plus 4b equals negative 11. So we're going to add 20 to both sides, right? And we get 8b equals, whoops, where did I lose? Oh, right here, be careful. Negative 5 times negative b is positive 5b's. Obviously, it only works right if you do your algebra right. So 9b's, add 20 to both sides equals 9, and I get b equals 1. Now I go up here, and if a plus b equals 4, and b equals 1, then a must equal 3. So therefore, if we go back up to here, we see that a is 3 and b is 1. So we went from this to this. And then we can integrate each of those things, each of those little tiny integrals. So therefore, 4x minus 11 over x plus 4 times x minus 5 can be rewritten as simpler rational expressions, 3 over x plus 4 plus 1 over x minus 5. So if we integrate this, we can integrate this. And we know the antiderivative of 3 over x plus 4 is 3 natural log of x plus 4 plus the natural log of the absolute value of x minus 5 plus c. All right, just a little side note. Your book tends to like to combine your logs. Remember, we can add logs by multiplying what's inside of the log as long as there's not a constant out front. So what I'm going to do is take that constant and create it as the power. So 3 times the natural log of x plus 4 is equivalent to the natural log of x plus 4 to the third power, natural log of x minus 5 plus c. And now that we have logs with no coefficients out, or the coefficient of 1 out front, I can change this to the natural log of x, parenthesis x plus 4 times cubed x minus 5 plus c. Okay, this answer is perfectly acceptable. This would be an alternate version of that answer. All right, so let's try a problem from scratch. We don't know the results we're looking for. All right, let's integrate x over x squared minus 5x plus 6. All right, well, let's first see if we can factor the denominator. X squared minus 5x plus 6 does factor nicely. This is equivalent to x over x plus 1, x minus 6, right? So let's just double check. Product of the first is x squared. Inners and outers give me negative 5x. Oh, nope, that's not right. Don't do that. So try again. 6 and 5 always can be tricky. So I have x and x. So what do I multiply to get positive 6? That was going to give me negative 6, but give me negative 5, and it would be negative 3 and negative 2. So that's the one we have to use. So we're going to rewrite this so we have distinct linear factors. So we're going to write it as a over the first factor plus b over the second factor. All right, so where we stand is x over x squared minus 5x plus 6 is equal to a over x minus 3 plus b over x minus 2. Now I have to solve for a and b. In order to solve for a and b, we have to add these two fractions on the right. So we have to find the common denominator, which is just the product of the denominator. So we're going to introduce the factor of x minus 2 to the fraction on the left on the right side, and we're going to introduce x minus 3 to the fraction on the right side. So this is going to become, my new numerator is ax minus 2a all over x minus 3, x minus 2, plus b, I'll do it right away, bx minus 3b, sorry, all over x minus 3, x minus 2. We don't need to redistribute because those denominators are just going to become irrelevant shortly. So this now is, my new numerator is ax minus 2a plus bx minus 3b all over x minus 3, x minus 2. So now we have that this is equal to x squared minus 5x plus 6. We set our numerator, those are the same denominator, so we set our numerators equal, and then we solve for a and b. So x is equal to ax, and I'm going to rearrange these right now to save a line, plus bx minus 2a minus 3b. So what we're going to do now is, we look at what's in front of x. So the coefficient here in front of x is 1. So a plus b must be 1. Because if we add a x's and b x's, it should give us 1 x's. So we get a plus b equals 1. And the constant term here that we don't see is plus 0. So negative 3a, nope, negative 2a minus 3b equals 0. We have to solve that for a and b. So last time I did substitution, I actually prefer elimination. I'm going to rewrite this. Well, if a plus b is equal to 1, then 2a plus 2b is equal to 2. I just multiplied the left and right side of the top equation by 2. And why did I do that? Well, the bottom equation is negative 2a minus 3b equals 0. And I'm just going to add down. So 2a and negative 2a cancel. 2b and negative 3b gives me negative b equals 2. And b equals negative 2. So you can do substitution. You would get the same result. Now we're going to plug that back in. A plus b equals 1. So a plus negative 2 equals 1. So a equals 3. So therefore, x over x squared minus 5x plus 6 can be written as a, make sure you put the right constant over the right fraction. When we go back up here, it's a was the value over x minus 3, and b was the value over x minus 2. Plus b, which was negative 2 over x minus 2. So now we can integrate both sides. So the integral of x over x squared minus 5x plus 6 is equivalent to the integral of 3 over x minus 3 plus negative 2 over x minus 2 dx. And we know the antiderivative of 3 over x minus 3 is 3 natural log of the absolute value of x minus 3 plus negative 2 natural log plus c, squeak that in there. All right, so now we can clean this up a little bit. This is a perfectly acceptable answer to me, but your book, I'm not quite sure how WebAssign wants you to answer. I'm thinking they'll accept this, but I'm going to rewrite this as the natural log of x minus 3 cubed plus the natural log of the absolute value of x minus 2 to the negative 2 power plus c. Now we can combine these two logs. This is just the natural log of the absolute value of x minus 3 cubed times x minus 2 to the negative 2 plus c. This could be concerning. It's not visually pleasing. So remember, this just means the natural log of the absolute value of x minus 3 cubed all over x minus 2 squared plus c. So either answer are perfectly acceptable. They mean the same thing. All right, so that's distinct linear factors. Well, things change a little bit if we have a repeated linear factor. So what do I mean by that? Well, here's my directions. It says, first, the degree of the numerator has to be less than the degree of the denominator. And if it has distinct linear factors as well as repeated linear factors or just repeated linear factors, it's the repeated linear factors which behave a little differently. So what we would do is, notice that this factor is x plus 6 times x plus 6 times x plus 6 times x plus 6 4 times. So what we would do is write this as the first denominator would just be x plus 6. The second denominator would be x plus 6 squared. The third denominator would be the factor but cubed. And then the last factor denominator would be x plus 6 to the 4th. And we stop when we hit the power. So however many times that factor is repeated, that's how many fractions it contributes to the decomposition. And then we just put the constants a, b, c, and d on top. So this is an example of a rational expression that has a repeated factor of x plus 6, no other factors, just the repeated factor x plus 6, which occurs 4 times. So this x plus 6 to the 4th is going to give us 4 fractions, each one increasing by a power of 1. If we had something like this, where we have 2 distinct linear factors as well as a repeated factor, we would have 1 fraction for each of the distinct linear factors. And then we would have this repeats twice, so that's going to contribute 2 fractions, and it's going to be the factor by itself, and then the factor, and you keep going up into the highest power, so there's only 2 of them, and then we would put A, B, C, and D. Now, I'm not sure if you're thinking ahead, but this algebra is going to get messy very quickly. So it just takes patience. Don't hurry. So let's try one with a repeated linear factor. So we are going to write, so we're integrating 1 over x times x minus 1 squared. So 1 over x minus 1 squared. Well, one denominator will have just the x. And then we have x minus 1 repeats twice. So that's going to have two contributing factors. So it's going to have x minus 1 and x minus 1 squared. And we're going to do A, B, and C. All right, so now here's where it gets a little bit hairy because now we have to add these back together, right? So we have A, and I'm just going to write it to keep it separate for a minute. B for x minus 1. Try to avoid a mess. Okay, so the common factors, well, this has x minus 1 squared. This only has one x minus 1. So this guy needs another x minus 1 in the denominator. Whatever we introduce in the denominator, we have to introduce in the numerator. So these both have x minus 1 in the denominator. This guy has an x. These two don't have an x, so we need x here, and we need an x here. Now this guy's missing both x minus 1s, so we have to do x minus 1 squared. Right, so the common denominator is x times x minus 1 squared. All right, so now let's hash this all out. This is my left numerator. Well, x minus 1 squared is x squared minus 2x's plus 1. My middle numerator is going to be bx squared minus bx's. And my third numerator is just cx. And that's all over the common denominator of x times x minus 1 squared. Now I'm going to distribute this a. I get a x squared minus 2ax plus a plus bx squared minus bx plus c. Oops, cx. Don't lose that. Changes the problem completely. Now I'm going to rearrange these terms. I'm going to put my x squared terms together. So ax squared and bx squared. And then so that takes care of that guy and that guy. I'm going to do my x terms. So I have 3 x terms minus 2ax's minus bx's plus cx's. And then all that's left is the constant a. Right, and that's all over this, but that's irrelevant now. So what I'm going to do is set this numerator equal to this numerator, save myself from writing. So it's just simply 1. But now we have x squareds and x's and a constant over here. So maybe this will help you see what's going on. 0x squared plus 0x's plus 1. So now I'm going to look at my x squared terms. We have no x squared terms on the left. So in a plus b must equal 0 because we want those x squared terms to cancel out. So a plus b must equal 0. I have 3 x terms, and that must also equal 0. So negative 2ax's minus bx's plus cx's must equal 0. And then lastly, a must equal 1. So we were handed a. A equals 1. Now this one actually is relatively easy to solve because if a equals 1, then b must equal negative 1 because a plus b is equal to 0. So now I can put a and b in here and solve for c. Right? So negative 2 times 1 minus b times negative 1 plus c equals 0. Whoops. What did I just do? Oh, here. That's silly. Negative b. This should, I lost this x here. Don't write that. So what I did is I mistakenly put the x here. So the coefficients, negative 2a minus b plus c must equal 0 because all those x's must cancel out. I accidentally put the x there, so I crossed it out. Now we're just replacing b with negative 1 and a with 1. So if a is 1, we get negative 2 times 1 minus b, which is negative 1 plus c. So negative 2 plus 1 plus c equals 0. So c must equal 1. So therefore, we're going to put it all back together up into this guy, and we get one over x times x minus 1 squared can be written as a sum of simpler fractions. It's going to be 1 over x, and then b was negative 1 plus negative 1 over x minus 1. And you could do minus if you want there. Plus c, which was 1. All right, is that what we got? Wow, that was pretty simple. All over x minus 1 squared. So now we integrate. And we know the antiderivative of 1 over x is the natural log of the absolute value of x. Right? This is going to be minus the natural log of the absolute value of x minus 1. And the antiderivative of, what's the antiderivative of 1 over x minus 1 squared? Now be careful, this is one of those situations that I said it's not going to involve natural logs because the function's not linear on the in the denominator. So what is the integral of 1 over x minus 1 squared dx? Well, this is a u substitution problem. And if you let u equal x minus 1, then du equals dx. So really what we're integrating is 1 over u squared du, which is equivalent to u to the negative 2 du. And the antiderivative of u to the negative 2 is negative u to the negative 1, which is negative 1 over u. So this is just going to be minus 1 over, well, u was x minus 1, plus c. That's it. Alternately, I'll just write the condensed version. So if you see it in your book, this is going to be the natural log. Well, we have the natural log of x minus the natural log of x minus 1. So that becomes the natural log of x over x minus 1. Can't do anything with that. No combining going on there. There's no logs involved. There we go. All right, so close. We can go on forever. Let's look at another case. Quadratic denominators. Degree of the numerator is less than the degree of the denominator, and the quadratic on the denominator is non-factorable and not repeatable. If the rational function in the integrand also has linear factors in the denominator, then we would just throw in the case 1 and 2 as well. So, for example, we would write, so this time instead, okay, so sorry, I jumped over this. The contributed term in the partial fraction decomposition would be the non-factorable quadratic denominator over the linear factor ax plus b. So here we have, if you try to factor these won't factor. So each non-factorable quadratic is going to contribute 1 fraction to the partial fraction decomposition. And instead of doing a and b, having constants in the numerator, we're now going to have linear functions. So we would write ax plus b, and then this would be cx plus d. Okay, and then we would multiply, find a common denominator, and solve for a, b, and c and d. All right, here we have the linear factor x plus 1 and the quadratic non-factorable quadratic x squared plus x plus 1. So we would rewrite this as, well, x plus 1 and x plus 1 squared, because the repeated factor, x plus 1 repeats twice, so that's going to contribute 2 factors. X squared plus x plus 1 is a repeated quadratic, so we're going to put it just by itself. And then we'll keep going until we run out of powers, and it goes up to the second power, so it's going to contribute 2 fractions to the decomposition. So now if your factor is linear, you just put constants on top. Even after we square it, if the original factor is linear and it's just being squared, we just introduce constants. If it's quadratic, we introduce a linear function. So even though this now is a 4th degree, we're just going to contribute C, D, E, F. That's what it would look like. And then you can imagine the mess. All right, ready? Let's try one. This might take a little while. So brace yourself. All right, look at this whole mess. X cubed plus 10x squared plus 3x plus 36 all over x minus 1 times x squared plus 4 squared. X squared plus 4 is not factorable. So we're going to write this fraction, x cubed plus 10x squared plus 3x plus 36 all over the linear factor x minus 1 and x squared plus 4 squared. All right, that's going to contribute just 1 fraction. And then the quadratic that's repeated is going to contribute 2. X squared plus 4 and x squared plus 4 squared. So this is a linear factor. So we're just going to add the constant on top. Quadratic factors, we add a linear fraction on top. Bx plus c and dx plus e. Woohoo! All right. Now we have to multiply this all together, right? So we have, I'm going to write this down, a over x minus 1. I'm going to give myself a little bit of room here, plus bx plus c all over x squared plus 4, plus dx plus e all over x squared plus 4 squared. Right, so this guy's missing the x squared plus 4 squared, x squared plus 4 squared, x squared plus 4 squared. This guy in the middle is missing the x minus 1 as well as 1 x squared plus 4. So we need to introduce x minus 1 and x squared plus 4. And then this guy's just missing the x minus 1. Now we don't need to distribute denominators. I'm going to focus just on the numerator because now this common denominator equals that. So I'm going to write that x cubed plus 10x squared plus 3x plus 36 is equal to a x squared plus 4 squared plus bx plus c x minus 1 x squared plus 4 plus, I'm running out of room, dx plus e, that's a d, times x minus 1. All right, so how are we ever going to solve here? All right, I'm going to tell you, I'm just going to write it out. I'm going to let you do the algebra in between. It's a little tedious, but it would just take way too long for you to watch me to do it. And what I land up getting is a x to the 4th plus 8a x squared plus 16a plus b x to the 4th minus bx cubed plus 4bx squareds minus 4bx's plus cx cubed minus cx squareds minus 4cx's minus 4c plus dx squared minus dx plus ex minus e. Yikes. So now we have to match that up with this guy. All right, so let's really take our time here. Let's look at the x to the 4th terms. Notice there's no x to the 4th terms here, but we have 2 x to the 4th terms here. So these two, a plus b, must equal 0 because we don't have any x to the 4th terms up there. So let's write that down. I want to make sure you have it in there. All right. All right, so we get that a plus b, the coefficients in front of x to the 4th, because there's no x to the 4th terms, have to equal 0. Let's now look at the cubed terms. I have a cubed here. I have a cubed here. Is that my only cubed terms? So negative b plus c are the coefficients in front of the cubed terms, and that must equal the coefficient of 1 in our original numerator. All right, now let's look at the squared terms. Let me get a different color. Squared terms. We have this squared term. We have 4bx squareds. We have some cx squareds. We have some dx squareds. So those coefficients, 8a plus 4b minus c plus d must equal the coefficient in front of x squared up here, which is 10. All right, I'm running out of colors. Let's do black. We're going to do black, and we're going to look at just the x terms. So the x terms, I have negative 4bx's there, negative 4cx's here, negative dx's, and 1ex. So negative 4b, the coefficient in front of the x's, negative 4b, minus 4c, I don't want to lose any, minus d, plus e, must equal the coefficient in front of x up here, which is 3. So now we have 5 equations and 5 unknowns. So this is quite an algebraic task. So all that's left is our constant terms, so that's what's left. We have hold on a second, where did I go with that guy? We have 16 A's, right? Minus 4 C's, minus an E. So that's all the terms that are left, right? And that must equal 36. Wow. All right, so you are going to solve this. And when you do, you can set A equal to negative B, you can set C equal to B, and you can start plugging away, do elimination. You should get A equals 2. I'm leaving this up for you to do. B is negative 2, and it should take you quite a while. Very easy to introduce, to make algebra mistakes here. So that's what that becomes. So my original integral, x cubed plus 10x squared plus 3x plus 36 all over x minus 1 over x squared plus 4 squared. We are going to write that as 2 over x minus 1 plus, we have bx plus c, so negative 2x minus 1 all over x squared plus 4 plus, and it's dx plus e, so it's just x over x squared plus 4 squared dx. All right, so how do we do this? Well, we're going to write this as 2 over x minus 1. This one's going to give us a little bit of a problem if we try to leave it like that because we can't do substitution, but notice we can break this up into 2. That's minus 2x over x squared plus 4 minus 1 over x squared plus 4 plus x over x squared plus 4 squared dx, right? So close, guys. Now I'm going to let you do the integration. I'm going to just tell you what the end result is. This is going to be 2 natural log of x minus 1. And then this is going to be, we're going to use u substitution here. When you use u substitution, you get minus natural log of x squared plus 4. This is just a trig. This is u substitution, and we can do 1/2 the inverse tangent of x over 2. And then I ran out of room. This is again u substitution. And we get minus 1/2 times 1 over x squared plus 4 plus c. Woo, that was quite a doozy. All right, one more little thing here. So here's some helpful templates. So again, you can do this using u substitution. Here's just the linear denominators. So we can just use these templates. If you have a constant over x plus a constant, this is what its antiderivative is. If you have 1 over x squared minus a squared, we can just use this template. And 1 over x squared plus a constant squared, we can use this template. So the very last thing in this section we didn't discuss is, what if the numerator is greater than or equal to the degree of the denominator? Well, we don't break it down into partial fractions quite yet. We can only use partial fraction decomposition if the degree of the numerator is less than the degree of the denominator. So how would we integrate something like this? And the answer is long division. So college algebra. We're going to long divide. I'm actually going to start on the next page because I don't want to break it off into and miss some of it. So let me pull that up here. How do we long divide polynomials? Well, hopefully you did this in your college algebra class. x cubed minus 3x squared goes outside, and 5x cubed, x to the fourth minus 5x cubed plus 6x squared minus 18 goes here. So then to do the long division, we say how many times does x cubed go into x to the fourth? What goes in, the factor that we would need would be x. So then we multiply x times x cubed minus 3x squared. So that would be x to the fourth minus 3x cubed. And we subtract that whole thing. And if you chose that correctly, those will cancel. So negative 5x cubed minus a negative 3x cubed, negative 5x cubed minus negative 3x cubed is negative 2x cubed. We're going to bring down the 6x squareds. And then x cubed goes into the factor that we need would be minus 2. So minus 2 would be negative 2x cubed plus 6x squared, right? And we subtract this whole thing. And we bring down 0, right? And then we bring down the minus 18. So this is the remainder. So then therefore, we would write x to the fourth minus 5x cubed plus 6x squared minus 18 all over x cubed minus 3x squared as x minus 2 minus 18 over x cubed minus 3x squared. But x cubed over 3x squared is x minus 2 minus 18. Well, let's factor, pull out x squared, and we get x minus 3. So then we are going to integrate this, which would be the integral of this, which would be the integral of this. And I'm going to let you do the work in between, and we get 1/2 x squared minus 2x, and then you break this up, use partial fractions here. And if you do that correctly, you would get 2 natural log of the absolute value of x minus 6 over x minus 2 absolute value, the natural log of the absolute value of x minus 3 plus c. So your to do is to fill in the work. All right, kids, these are tricky, very time consuming. So have fun, good luck, and zoom in with some questions. See ya.